Dear students, welcome to Statistics and Dynamics with me, Dr. Loay Al-Zube, and thank you for tuning in to this video. This is the second video of our lecture about free body diagrams. We are still talking about the statics content of the course. In the previous video, we stopped on how to construct a free body diagram, and we used the example that is seen on the screen. So we talked about imagining the particle to be isolated or cut free from its surrounding, and that's point A here. And the idea is, can we find a free body diagram that can help us identify tensions and forces and the different cables that are found in the planar system that we are looking at. And also we talked about showing all the forces, active and reactive forces, as well as identifying all the known magnitudes and directions and the unknown magnitude and directions, which are the variables that we are going to solve for. We would like to go into constructing the equations of equilibrium for this system as an example. So remember that we are going to build a free body diagram and then construct equations of equilibrium in order to solve for unknown variables in any system, assuming that the system is at equilibrium. And that's what we have in our example here. This is how we build the free body diagram. So that's the weight going down. So the directions are very important. That's the tension from AD going to the left and the tension from AB going to in the direction of the positive x-axis, but it's off with 30 degrees from the positive x-axis. It's very important to have your directions and notations correctly, which direction is positive and which direction negative in an x and y Cartesian coordinate system. One more thing to note is that if you look at point A here, you can see that we have this ring. That means that all these cables are independent cables, which means that the forces in AD is different from the force from AB and different from the force from AC, which is the force FC. And we're going to look at this again when we talk about pulleys and how cables and pulleys actually work together as opposed to this structure here. So let's see if we can construct the equations of equilibrium. So let's say this is our free body diagram. Let's move on to the equations of equilibrium. The question here is to find FB and FD. What are the tensions in the cables AB and the cable AD? So that's what we're looking for to identify. We start with our free body diagram that we have constructed. So again, these are the forces known. This FC is a known force, which is the weight in kilograms multiplied by the acceleration, gravitational acceleration, which is 9.81, and I have two unknown forces, and I have the angle with the positive x-axis and the FB. So since the particle is at equilibrium, that's our assumption, the net force at A in all directions should be 0. If we added FB plus FC plus FD, the three acting forces, they should all equal to 0. And remember that all the forces, they could have two components. If this is a planar system, a two-dimensional Cartesian coordinate system, we will have a component on the x-axis and another component on the y-axis. If we have this formula in mind, then the summation of forces on the x-axis should equal to 0, and the summation of forces on the y-axis should equal to 0. And that's how we represent our two scalar equations of equilibrium. So if we are studying a two-dimensional system, we need to construct two equations of equilibrium, one in the x-axis and the other one on the y-axis. So you need to project your forces on the axes first, and then you sum all the forces on the x-axis. They should be equal to 0. Pay attention to the directions, positive and negative, and then you sum all the forces on the y-axis, and they should equal to 0. And that's how you construct your equations of equilibrium. Since this is a two-dimensional system, we can come up with two equations, and this will allow us to solve for up to two unknowns. That's how we construct and solve the equations of equilibrium. Keep in mind, our assumption is that we are at equilibrium. Let us construct the equations themselves and see how would they look like and what can we do with them. We'll keep the same system. This is our system that we started with, and this is our free body diagram, and we said that we have all summation of forces on the x-axis should equal to 0 and summation of forces on the y-axis should equal to 0. Let's start with the x-axis. I'm going to assume that the direction to the right is positive x-axis. So the summation of forces on the x-axis, all of them should equal to 0. So I have how many forces do I have on the x-axis? I know that I have the FD first, and its direction is to the left toward the attachment of the wall, and so it's going to be negative. And I have force FB with a 30-degree angle off the x-axis, the positive x-axis. So I need to project this into its two components and resolve it into two components, the x component, the y component. If you remember from the class, we mentioned that if the angle is off a particular axis, the cosine component will be on that axis. So in the x component, it's going to be FB cosine 30, and the one on the y component is going to be FB sine 30. So if I'm looking at the x-axis, I will have FB cosine 30 minus FD should equal to 0. And that's the first equation of equilibrium. Now going to the y-axis, we can see that I have the FC going down. And if you remember, FC is the weight of this cylinder, which is 40 kilogram multiplied by the gravitational acceleration, which is 9.81. And it's going down. So we're looking at the cable, right? So it's going pulling the cable down. So that's negative FC. If you remember from resolving FB, we said this is FB cosine 30. This one is going to be FB sine 30. So we will say FB sine 30 minus the 392.4 Newton should equal to 0. Now, these two are actually our set of equations of equilibrium. There are two of them because we are talking about two-dimensional system. If we have a three-dimensional system, we're going to construct three, where we will have another third one is going to be summation of forces on the z-axis should equal to 0. But we're not going to do this for this example because it's a two-dimensional system. So two is what we should be constructing. Now, if you look at the system of two equations, we have two unknowns, FB and FD. The problem that we started with is can we construct a free body diagram, and can we get the tensions on the cables AB and AD. We can do substitution and elimination to get the forces. So I can use the second equation here, which has only one unknown, FB. I can move the minus 392.4 to the other side is going to be positive, and then divided by sine 30, and then I'll have FB to be 785 newtons. Substitute FB into the first equation, and you can get FD to be 680 newtons. So this is how we actually analyze static systems at equilibrium. Step one, you need to build a free body diagram or come up with a free body diagram. And then you need to locate all the known and unknown forces. And then you need to resolve your forces into x and y components, the Cartesian components. And then you need to construct your equations of equilibrium, saying that the summation of forces on the x-axis should equal to 0 and summation of all forces on the y-axis should equal to 0. And then you do substitution and elimination to find your unknowns. And that's what we did for FB and FD. So this is a quick example about how we use, what are the applications of free body diagrams and how do we use it in constructing the equations of equilibrium. A couple of things we need to mention before we finish this lecture. The first one is talking about a new force that we're going to be using frequently, which is the force of a simple spring. So if you remember from physics, the spring force equals the spring constant multiplied by the deformation of the spring. So if you have a spring and we are pulling it down with the force F, this F is actually proportional to the displacement by the spring constant. And so you take the initial, so the final length minus the initial length, and that's give you S, and you multiply it by the constant, and that's what's your spring force. Remember that the spring constant is mainly a material dependent quantity. So if you have different materials, let's say stainless steel, or this is made of iron, or made of whatever metal it is made of, each metal will have a different spring constant. So you will see a lot of these springs in our statics problems that we need to solve. So just keep in mind that the force in the spring equal to the spring constant multiplied by the deformation of the spring. And you will probably be giving these quantities. Okay, one more thing we need to mention is the frictionless pulley and cables. That's an important concept in analyzing statics problems. So if you have system like this, and this is the pulley here, a frictionless pulley and cables, we have two tension forces around it on the cables, and T1 and T2 should be equal as long as this is a frictionless pulley. And we're going to use this in a lot of problems. So if you see such a structure, you know that the T1 and T2, they're equal quantities. And keep in mind that the cable can support only tension or pulling force, and this force always acts in the direction of the cable. So I wanted to just to make sure that we are on the same page on these concepts, so that when we solve problems in the in-person session, we are all, on the same page. Thank you for watching, and till next video. Bye.